normally a very honest person, but the truth of the matter is, this museum is Carol Willis. It's not, the rest of us sort of dabbling around the outside. We had very little to do with it. She was the boss. No question about it.
I be boss.
And I can see 1, 2, 3, 4 empty chairs up here. If
Yeah.
anyone wants to sit down, please run up there and do it.
Hey, Kyle,
There you
come
go.
on.
You know, I'm
Okay, 2 more
89
chairs
years old,
in the
so
front.
I like to sit down. There's still more.
One more chair in the front. Yeah, move up, and then there's one in the back here. Okay, well, we'll let you figure out the back. Okay, go ahead.
So anyway, last night I'm on a mentoring group for the American Society of Civil Engineers, and we had about 30 engineers from middle range to lower middle range to beginners, even students who were in our mentoring program. And the question and answer period lasted 1 hour and 37 minutes. So we finally got home. Anyway, my advice about places like this, you should sit near the door and have a fast car outside so you can leave whenever you want to. Okay, so I guess I have a tool here to change these. We've done all kinds of buildings, and this is a tall building place, and so I was reluctant to put in all the outhouses that we do. So mostly on the higher range. This is architect was Curtis and Davis out of New Orleans, and the interesting part was the steelwork was very unusual, both the design and the material itself, both very unusual. And when the shores were being taken out from underneath this building, the place was packed with reporters thinking it was probably going to fall down. Actually, there was a rumor around that it was going to fall down, but of course it did it. But and it's very redundant. But I think it was 1965, something like that, when this was done. Now it has a name. It's called a diagrid, isn't it? I think, yeah. We didn't have a name for it. It was just a truss. But same structure. And you see, the United States Steel Corporation painted the really high-strength steel red, sort of middle-range blue, and lesser strength yellow. And traditionally, all engineers had designed by starting out with the yield point of the steel and the loads and moments, and then select a section. This design was done exactly the opposite. We selected the section, and the answer was the yield point. So a different kind of approach to design. And the calculator was 11 ladies with desk calculators. So as prefabrication was big, the largest member in this building is a 6-inch angle. There are 2 supports on each of the 4 walls underneath the whole structure. Following this building and a couple of others, Minoru Yamasaki came along. Didn't come along to me. Came along to John Skilling, who was a great, very creative guy, and with a golden tongue. And this photograph was taken by Taro, his son, who's a Pulitzer Prize-winning photographer. Wonderful guy, and a wonderful family. I knew Yama very well. I knew his first wife and his last wife, which happened to be the same person. So this is the first building I did with him. It's an unusual building. It's all reinforced concrete building. And my idea was to take Yama's idea of having narrow windows, a place you could put your hand on both sides, and to put inside there the structure. And the structure for this building in the perimeter is 4-inch pipe columns. But again, same thing. High-strength steel. Oops, I don't know how to operate this machine. High-strength steel at the bottom, and then progressively lower strength and thinner wall pipe. A really well-known engineer, and I was giving a tour of the building, talked to me about why didn't we have expansion joints in the mullions. And he thought that those columns were mullions and that the floor is cantilevered from the services core. learn a lot about communication. Anyway, the base is also steel, but clad in stone, of course. World Trade Center came along, and again, our John Skilling was the sort of genius that got us to work. I had a little office separated from the main office, and four of us total, worked on making boards and ideas of what kind of structure to use, and on and on and on. We worked on it for a couple of months. And then John and I went to New York to make a presentation to the Port Authority. John Skilling is a very smart guy, and he made me shut up, and he made the presentation. He did not show a single board. He did not talk about the structural system. He had one subject, and that's how he, John Skilling, could get Minoru Yamasaki to build a practical, buildable building. And that's what the Port Authority really wanted to hear. And, you know, those of us who were ignorant, we had no idea that was even going to take place. He was a wonderful man. And we took wind engineering into a new form. And by we, I mean actually basically Alan Davenport and I. I went to London, to Teddington, to the first Wind Engineering Research Council, and listened to all these wind engineers talk, and I was bored to tears. I was about to leave. And then Alan Davenport got up there, and he was like, he knew more than all of them put together. So, not being completely stupid, I went to him and said, Alan, we have a job for you in this World Trade Center. And he was a professor at the University of Western Ontario, but he took a one-year leave of absence to work with us on it. Fantastic experience for me. Our computer was called a Cadet. We figured that Cadet meant can't add, didn't even try, because if we wanted to add 3 to 4, it would 4 here, 3 there. There was 7 in the table. And it did multiplication by multiple addition, and etc. But this machine right here is a disk drive about the size of a small washing machine. You know, different world at that time, but it was solid state. Man, IBM's first medium scale solid state computer. And we did everything on the computer, much more so than I would have imagined when we started out. But every piece of steel in the project was given in a digital format. This is a printout of a digital format. Keep printing on the button. This is a printout of this particular wall panel. And it gives the width, thickness, grade of steel of every piece of steel in the exterior wall, all the floor beams, everything, all done digitally. And our contract said that the contract was based on the punch cards, because there were no tapes, it was all punch cards. And Port Authority lawyers objected. Nope. And they sent a message around saying, no, the contracts can be based on the drawings. And the hue and cry from the contracting industry was incredible. They backed down. Amazing. First time I've ever seen a lawyer back down in my entire life, actually. Push that button. I didn't know anything about tall buildings, and as a matter of fact, very little was known about really tall buildings. And I got interested in about the fact that the outside air in the wintertime is cold and the inside air is warm. And I knew that that meant that air would come into the building at the bottom and rise up through the building. What did that mean? I didn't know. So I got on top, I got con developers or owners to let me ride on top of their elevators, and so I could see out how tight were the walls. They're all gypsum block. And they leak like a sieve. I mean, there was just an incredible amount of air being able to travel right through those shaft walls, as the saying goes. So another of our, I wasn't an engineer, actually I was an architect by training, and I developed a partition system that was made out of metal studs and gypsum wallboard. And it was built from outside the shaft, whereas the block walls were all built from inside the shaft. So it eliminated all that scaffolding. And airtight and light tight, and saved a whole lot of money. And pretty much that kind of construction is a traditional construction today. Prefabrication, some pretty big pieces. Here you see a person. These were all made in Pittsburgh. Again, all 100% of the design of that piece is given in digital format to the contractor. It was done by Pittsburgh Des Moines, a very competent fabricator. And here you see them coming into New Jersey. Nothing was small about the Trade Center. Everything was huge. So you kind of had to get used to it. Port Authority one time decided to take some of the floor panels and transport them by helicopter because the barges were very slow. Never got one clear across the harbor because they would start oscillating in the wind and the pilots would drop them. And so the harbor has some of our structural steel inside of the harbor itself. This is a typical wall panel. It was 3 stories high. Everything up to that point in time that I knew of in structural steel was a 2-story module. We went with a 3-story module so that, and we had splices here and there, but the panel next to it would have a splice at this level and up here, and the panel next to that one at this level and above. So all the splices were staggered, if you will. So had a kind of redundancy. A kind of redundancy that was that really worked for the project. Anyway, this is a picture taken giving you an idea how really open the structure was. You're looking right through the finished building. Then, while we were hot at that one, United States Steel Corporation decided to build a corporate headquarters in Pittsburgh. And, they retained Harrison Abramovitz, who'd done Rockefeller Center, and all those. They were top dogs in that world, I think, at that time. And a structural engineer who was equally familiar with all of that. But I guess the upper echelon members of United States Steel Corporation decided that they wanted me to do it. And because things like that first building I showed you, the Curtis and Davis building, that sort of thing, and others, and the World Trade Center. And so, unbeknownst to us, they released that engineer, and we got the project. This is Max Abramovitz. Max Abramovitz right here. We looked for a picture of Max, and we have some of it, but I couldn't find it. Actually, I is the wrong word. Saltine couldn't find it, because she's much better at finding things than I am. So she couldn't find one. But, this is, he's accepting an award from the United States Steel Corporation for the largest privately owned building in the world. And here you see it. And the interesting part about this building is the relationship between the structure and the architecture. The architects wanted to build a triangular building, a pure triangular shape. And the developer, Galbraith Ruffin, wanted to build a rectangular building. And I didn't like the triangle because it's a very bad aerodynamic shape. And so I proposed this. I said, well, if we notch the corners, we could build 3 rectangular buildings, have 6 corner offices instead of 3 or 4. Anyway, it was an easy sell. It was amazing. Well, there were tough times. And the United States Steel Corporation wanted to put the columns outside of the building and no cladding on them. No cladding whatsoever. So their idea, not mine, their idea was to water fill the columns. So this is the largest collection, I think, of rectangular pressure vessels on the planet. It's and say its water is a stretch. Specific gravity 1.2, which means it had antifreeze, corrosion resistance, and all that stuff. By the way, am I talking loud enough? Louder? Yeah. Louder. Okay. I'm generally a soft-spoken guy. Anyway, 2. And they wanted to put the columns 13 feet on center on the outside wall. And I thought, well, 13 feet, that's a lot of columns. And each time that column had to have a connection back through the curtain wall, and I was seeing a kind of little horror story there. So I suggested instead of 13, why don't we make it 39 feet? And actually that went over pretty well, most of them. Yeah, that got along very well. But then I said, okay, instead of connecting the columns to the building every floor, why don't we connect them every third floor? So now you have 1/9 as many connections through the curtain wall. And that was a much tougher sell, but it worked. We actually got it through. And in the process of all that, you know, the building shape was very important. This is a pure triangle, rectangular building, round building, square building with notch corners, and a triangular building with notch corners. And not being completely stupid, I made ours the best looking model of all of them. So anyway, they bought our design for this one. And the technique for connecting the columns every third floor was this. We just connect the column here and we connect the column there. And then if the column's not exactly straight, which it never is, of course, we don't have to worry about that because we can line it up at the top and at the bottom. And we use little 6-inch wide flange columns to carry down to the so-called major floor. And it was great fun. You could, if you were brave or stupid, you could sit here on the edge, dangle your feet over the edge, and point out to your guest, if you could get him to do this or her to do the same thing, that the column wasn't connected to the building. And then I say, oh, we cantilever the floors, of course, and people believe all kinds of things. But anyway, so it was kind of interesting, and was put up 3 floors a week, which is pretty good for a building pretty much an acre in size and the largest in the planet. Using ancient guide derricks, really old equipment. In the corners of the core, there were very big columns because we had train tracks running through the building, and so had to take out columns and offset. Some of these were offset, and these are called hybrid columns. That is, we used higher strength steel out here and lower strength steel in the middle because we couldn't get high strength in this kind of thickness plate. And we didn't have a problem selling it to the building department because the building department never checked the plans anyway. So it was, at that time, New York you didn't submit the drawings to the New York City building
We should move
department.
into the picture, the
Oh,
field.
sorry, I'm marking away from it. So we didn't have to submit anything so we checked ourselves at first. So the facade kind of looks like this. This curtain wall was a patented design owned by the United States Steel Corporation. The bottom line of this is that the shape of the building, the organization of the columns, the 3-story module, the curtain wall itself was all done by other than the architect. Now, I confess the building has too much less Robertson and not enough architect in it. I mean, I'm quick to admit that to be the case. But at the time, I was pretty enthusiastic about it. maybe more so than I should have been. So now it's no longer the U.S. Steel building. They've sold it, and there's been a move afoot to put on top. The roof is designed for vertical takeoff jet aircraft. United States Steel had the largest privately owned airline on the planet. So I don't think maybe an occasional helicopter, but only very occasionally actually landed on the building. But anyway, the idea was to put a museum, observation deck, et cetera, et cetera, et cetera. The problem was to get people up there, and there's a big mechanical space up here and all kinds. So it was difficult, and it's never happened because the developer didn't want it. So didn't get it done. So this is the Gunnar Burkerts. Unfortunately, he passed away just a month or so ago. And his wife Sylvia. We're kind of real old friends. We used to go to their house in north of Detroit on Christmas time fly up on Christmas morning and fly back on Christmas afternoon and have Christmas lunch with them. So we're kind of old friends and did a lot of buildings with Gunnar. And he had a wonderful soft voice and I think not very well recognized in the architecture profession, but anyway, he was fantastic. So he came to our office one day without an appointment. He just arrived and this is what he had in mind. He was going to do this Federal Reserve Bank in Minneapolis, and he had the commission to do it. And we chatted a little bit, and then he said, "Of course, you know my work." And I said, "Gunnar, I never heard of you before in my life." Never heard of you. I mean, I'm very, let's say, frank with people. I mean, I know how to compliment a not so pretty lady, but I'm not averse to being polite. But when it comes to something serious like buildings, I'm brutally frank. This thing goes. His idea was to have many catenaries to hold up floors. And I worked with him about what catenaries are supposed to do and so forth, and eventually convinced him that a single catenary was plenty and much better, actually. Saved money and time and simplified this construction. We'll come back to that. So the design ended up like this, a catenary and a truss at the top. So the catenary puts that truss in compression. Later on, the bank said to me, you know, the only thing we worried about on this project was the structure, and it's the only thing that really worked. So Gunnar's next idea was to build, for future expansion, to build another building on top of the original one. And it clear spanned also. That is, there's a gap here, and this catenary puts compression in this truss, and this catenary puts a tension in the truss. And the two forces are more or less exactly the same. So it kind of, when you build the future expansion, you relieve stresses in the building. Sounds simple, but you have to design for the fact that stresses are being relieved. Anyway, and this is Gunnar's representation of that. And the catenary looked like this, a 36-inch wide flange. And we talked about one on each face, we talked about one down the middle, and of course his original ideas had many catenaries. We explored all the possibilities. This, you see, the 36 wide flange and the catenary's post-tension. So when the structure was finished, this catenary was slightly in compression, not in tension, because the tension was carried in the post-tensioning, not in the 36-inch wide flange. And Gunnar's brilliant idea, I mean, it's incredible. I should bring you back up one. You see, up here where this wall's all in compression, we use wide flange columns that come down and sit on the catenary. And down here, where the wall's in tension, we just use a single plate, perpendicular to the plane of the wall. So it allowed for the construction of a very kind of tense all-glass wall in the tension part, and a relief with the columns on the compression side. And I think it really made this building super incredible. But it's been fun. The building's been sold, and across here is a clear span. There's no columns inside of that space at all. But the developer put a shopping center inside there, so now it's all closed off. This is Ian and me. Ian and I have lunch more or less every other week. Just the two of us, we get together. He has a wonderful wine cellar. We have wine, and Diana is the lady who looks after him and provides a wonderful lunch. And he's 100 years old, or a bit more than that now. And fantastic man and a dear friend. his wife, Eileen, she passed away a few years ago, and she taught me how to shuck oysters. I mean, we were very, 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 very good friends. And I did several projects, but this is the most striking one, I think, the Bank of China Tower in Hong Kong. He called me on the phone, he said, well, I have this project in Hong Kong. It's a high-rise project. Why don't you go and let's talk about it? So, naturally, I did my homework. We did, I think, 18 buildings in Hong Kong, but all low buildings because of the Kai Tak Airport and height limitations and things like that. So I knew a lot about the wind loads and about the wind and climate in Hong Kong. And we would see him, not really worried about it very much, but he had a model. It was an opaque model. It didn't have any architecture to it except the shape. And I realized that it is a very eccentric. That is, much of the building this is a quarter of the building, is way off on one side, so very undesirable from the point of view of the structure. And so I proposed bracing. I think it probably took him, a full half second to say, that's a good idea, we'll do it. But I was incredibly sharp and perceptive about most everything in life, I think. Particularly his wife. His wife was fantastic. So anyway, the first big obstacle came up because in Hong Kong you have what are called refuge floors. That is, refuge floor is where there's nothing that's combustible, and the fire stair comes down, 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 arrives at the refuge floor, and empties onto the floor. You can get in another refuge floor, stair, and go down. So it's a continuous stair, but always terminates at a refuge floor. And so this is Iam's idea of how the bracing would work. We took this to Hong Kong, and the bank they had a model and see in advance. And they said, we think the structure is wonderful, we want to use it, but bury it. Don't put it on the outside water where you can see it. Because the X is a symbol of death, and we don't want that on our building. So most architects would have a temper tantrum, but we went back and sat around in his garden, drank wine, and talked. And we talked a lot about bridges, and I pointed out that these refuge floors were not really very important in the structural design. We could live without them if you could, but you can't. So he then said, okay, well, get rid of this and that, and it looked like that. And then we went back to Hong Kong and met with the executives of the bank, and he explained that these were diamonds, not X's. They said, okay, well, we're a modern organization, so we'll do it. No more talk about the structure. That was all it took to get it there. The golden tongue of the Iron Peg. There was at that time, almost no safety protection for people working in steelwork. So people, you see these guys are wearing sneakers instead of hard-toe shoes, and they're not tied into anything. It's all very, looks very dangerous. But in fact, the death rate was rather modest, although it started out bad, but it got better right away. We call this an elevator. And your eye is immediately taken to these three guys standing up here. Casually, they're holding onto the rope, but they're riding this elevator up. But look at this guy down here. He's not tied into anything. He's just working, doing his job, and can't do that anymore in Hong Kong or any place else in the world that I know of. But probably there are places you can do it. What it's worth, we're the engineers for all the buildings over here on the far side. And again, you see, this is the superintendent of this ironworkers. And he's standing on a bare steel beam lassoing this big piece of steel. And this guy looks like he's in a bosun's chair, but if he slips, he goes straight to the ground and on. With the topping out ceremony, to my astonishment, he dragged me out of the crowd and gave me the golden bolt, the last bolt, so to speak, that goes into the project. It wasn't gold. But anyway, it's finished, and I think it's extremely handsome building, as Carol pointed out. It's a wonderful design and done by a wonderful man. So this is Philip Johnson, and if you want to talk about two architects who are very different, I would say Philip and John and Ian were about as different as you could imagine two people to be. I don't know that Philip had friends. I mean, he was a very cool guy, extremely smart, very verbal. But he and I often spent 2 hours, sometimes 3 hours, just sitting around looking at picture books, turning the pages and talking about what was inside and how it affected architecture and structure and planning. And it was a real pleasure to work with him. I mean, I could put aside all of his Nazi, early Nazi leanings and all that sort of stuff. I really liked Philip a lot. So we did this project with him, and I wasn't there, but apparently he was talking to the developer for the building on the right and the developer for the building on the left, and they were having difficulty having to decide how they would split the project between the two of them. And as I'm told, Philip put his elbows on the table like this and did this. And that was his total contribution to the project. It was enough. It was enough, I'm sorry. It was an incredibly intelligent guy, and he had a lot of great help, obviously. So, yeah. And the building's very simple, and basically it's concrete core steel frame building. So one of the problems is the building's lean. I mean, it leans, right? How do you make a building that leans like that? Because when it leans farther, right? You have the gravity takes hold of it and it moves along. And the building is built 50 millimeters, 2 inches off the property line. So it moved very much. It was on somebody else's property, which is not a good idea. And I had meetings with the mayor, and et cetera, and on and on. But anyway, I made this proposal as not a serious way to do it, because I never would imagine doing that. I just pointed out you could build a building, and I use it here because if this were the building, it doesn't have a tendency to lean at all. And if you put a weight here and a weight there, they're equal, it has no tendency to lean. So that's right. So if we take this weight, pull it up to there, and this weight push it down to there, you have a leaning building that doesn't lean. Doesn't lean under gravity, is what I'm trying to say. So we didn't do that, of course, but we used this close tensioning. What we did is we built a concrete core and a steel frame and et cetera, and grab hold of it with both tension tendons and pull it back. And by adjusting this eccentricity up here, this puts a bending moment, which is this way on the core, and the wind push and the gravity pushing that way puts a moment that way, and we can make the two equal. So this structure doesn't have a tendency for long-term displacements under gravity, and you have laser plumb bobs and it doesn't, in fact, display. So anyway, it's called Puerta de Europa. We've got several buildings in Madrid. This is the most exciting one. These are the most exciting, I should say. And now we turn to the far east. This is Bill Everson. I don't think he designed that chair. He's not here, is he, by chance? No. But he's a chair designer also. And amazing how many architects we work with who do chairs and tables and all kinds of furniture. Furniture and architecture are somehow related. And so we're sort of constantly involved in furniture design. Crazy work. Love working with them. Great people in the firm. So the finished project looks like that. You notice in this early rendering there's a round hole at the top, but it wasn't built like that. And that's because the mayor of Shanghai said, it looks like the rising sun of Japan over Shanghai. We're not going to have that. So anyway, Bill came up, I guess, or someone came up with a better way to do it. Tool here. But when the project first came along, it was to be a given height, et cetera, and that's shown in green. That is, this is the original building height, this is the original floor area of the building, and the developer wanted to build basically 9% higher and 16% more floor area. Oh, and by the way, you had to use the same foundations. And I guess of course he went to Japanese engineers, as any sensible person would do, and for whatever reason, he didn't get an answer that worked. And eventually we got a job to design the project, the bigger building on the old foundations, because the relationships between China and Japan are not exactly friendly. They're compatible is the right way to put it, but there's not a homey relationship there. So we were able to use the old foundations, put the bigger building on it, bigger, taller building. And so it worked for us and it worked for more building company. This is a photograph of the model. A lot of discussion with experts in China about bracing. They saw it one way and I saw it another. And we had our moments, is the right way to put it, probably. The original design had been done by other engineers, and it used closely spaced columns, sort of like the Sears Tower in Chicago. So the outside wall looked like that. Not too great, I thought. So our design looked like that. That is a lot more open, a lot more glass. And the secret to success, got to stay close to the camera, sorry. Secret to success was to take a lot more stiffness in the perimeter so we could take a lot of concrete out of the interior of the building. So we could build a bigger building on the old foundations. So this is pretty open. You see the columns. This is a diagonal brace. This is a column. Columns are pretty small, just almost deflection posts. But the structure was massive. I mean, this is a really big building. So this is the corner. And notice that the bracing is here, but there's no connection between the bracing. It's in this plane over here and the one in this plane over here. They're not actually touching. But they are encased in the common concrete, and so we use the concrete as a technique for taking this frame and making it work with that frame perpendicular to itself without actually connecting the steelwork to one to the other. Just as we had done, by the way, on other buildings. So it has this surface that keeps getting wider and wider and wider and wider until the building is a single line across the top. And it looks like that. It's pretty significant. I think, architectural statement. Beautiful building. And then move on, and here we see yet another architect. Is he here tonight?
No.
Anyway, it's the building. It's a low-tech tower, and it's, I would say it's extremely, pardon?
So who's the architect? Who's the architect?
Jamie.
John Klemper is the architect of Cone Patterson Fox. Sorry about that. Yeah, Jamie's not here either.
No.
I saw him yesterday. Lotte is a very complicated organization. They're retail, they do everything. They do everything. And they ended up being the contractor, and in many ways they were the engineering and on. The chairman of the board was, not sure he was Japanese by race, but certainly he lived in Japan and was Japanese was his native language. But you see very elegant forms. And this is just opening day, just the night before fireworks from the building. It's a magnificent sight. And this is taken in Hawaii, on Haleakala. And it's an untouched photograph. So anyway, even stuff for you, there's a bridge we did in Japan.
Mike.
Oh, I'm sorry. This is a bridge we did in Japan, and it's called Miho Bridge, and it's a post-enter steel design. IMP was the architect for the museum, and I say he was also the architect for the bridge. He won't admit it. He says, I'm the architect for the bridge, but it's our bridge, maybe the right way to put it. It won lots of awards, and it's an extremely handsome bridge. So if you have any questions, I'll keep the microphone in there. Anyone knows how to raise his hand? There you go.
With regard to the Madrid design, which is terrific, do you have any comments about the CCTV building in Beijing, which is not trying to balance, but is trying to tip over, basically? So your building, you emphasize the balancing effect of the Madrid building, but I just wondered if you have any side comments about the other buildings that had no connection with it.
No, we have nothing to do with the building. I mean, I think that in the architecture world today, there's a lot of stuff going on that's rather unusual, and structural engineers get dragged along just like the mechanical engineers and the contractors, and we do it. But I mean, I'm not an enthusiast of that kind of thing, but I think it's an exceptional building, by the way. Is there another handout?
I was going to ask if you would just explain the bridge a little bit more.
Oh, well, I'm in the Skyscraper Museum, so we'll read. Okay, well, the concept is very simple, and that is the land down here is so-called sacred land. It was trees were harvested from here for temple building in Nara. And so we had several rules. One is that you couldn't put anything on the ground. So idea was to use the tunnel. This is a tunnel back here, and tie these cables into the tunnel, and then cantilever from the tunnel as the foundation for the bridge itself. Now, the designers of the tunnel were rather upset. He said, we were trying to pull the blooming tunnel out of the mountain, and it's not designed to be pulled out of the mountain. And I was able to convince them that the compression at the bottom of the tunnel and the tension of the cables was exactly equal, the horizontal component, that is. So there was no outward pull on the tunnel at all. So that was pretty easy to get over. The other thing is that
the largest piece of steel in this building is a pipe, a small pipe. And the drains to get water off of the bridge were bigger than the structure. So I propose that we use a kind of a porous deck for the bridge. Now, C.G. Schumacher's organization was not going to have anything where you could see through because they felt that was incompatible with the people of Japan. And probably they're right. I'm sure they're right. They would know more than me. So this deck is absolutely opaque. It's made out of little plastic pebbles that are sort of glued together, but it's a permeable deck. There's water rains on the top and rains right through. But you can't see through it at all. It is opaque. And it's a very elegant surface. And the way to get it through was I had lunch a couple of times with the biggest grading manufacturer in Japan. And we did business the Japanese way. We had a lot of beer and sake and lunch. And he agreed that we could try it and made mock-ups and all that, and eventually showed it to the client and to who it was to pay. And everyone thought it was beautiful, but contractors still required freeze-thaw tests, all the things that contractors should ask for, they got. And it worked. And where the idea came from, I was playing tennis in Florida. And it was this tennis court, and rains, tropical place, it rains, you get a short burst of rain and it stops. And the players would go out and start playing on the court immediately. That's because it was porous. It was a porous surface and very high friction. It was not like a clay court we could slide. Definitely not like that. So this is very good too because this bridge is used largely by pedestrians. Large numbers of pedestrians. I don't have a photograph to show you, but we have a photograph showing this bridge absolutely jam-packed, elbow to elbow, full of people. And they use golf carts to take handicapped people. How are we doing for time? You okay? Yeah, they use handicapped people go on golf carts, so you could hear the golf carts because the surface is sufficiently rough so that the sound of the golf cart can be heard by the people who are walking away from it. So it's been a very successful surface. We actually, if you come out to we have a little house in Connecticut, we have a sample out there, you can see what it looks like. Beyond these cables, there's another set of cables, which are these, which is we call it a king post, this right here. So the bridge is supported by cables out to here, and then here, and then on the abutment on the far side. Pei and I were standing over this end, looking back this way, towards the mouth of the tunnel. And at that time, there was a concrete head wall laid back against the earth. And I'm reluctant to go to kind of name architect and voice my objections to the architecture work done by staff. I try not to do that, and I did. I bitched to staff a lot about this concrete head wall because I thought it was ugly and awful. But anyway, when I were standing over there, I said, gee, wouldn't it have been nice if we didn't have that concrete work? He said, yeah, well, we needed it for erosion control. That was the opening I needed. I said, that's not erosion control, that's your design. He walked across the bridge, take it out. I couldn't get that to happen, but Brian Pei could get it to happen.
Yes.
How high can you build? I mean, will we ever see a mile-high building?
Of course.
So what are
Yeah, first you're going to see a mile-high building. How high can you build? Well, NASA was proposing building a structure to space. Okay? So that instead of putting things in rockets, they put basically on railroad cars in my mouth. Slight exaggeration there. How do you do that? Well, first of all, there's only one place to build it, that's on the equator, because the Coriolis effect, that is the rotation of the Earth, would put big bending moments on anything that cantilevers. Higher the cantilevers, the more effective Coriolis forces are. So it has to be built on the equator. So if you want to build a building to the moon, you start at the equator and go for it. And I don't know of any physical limitation. There are a lot of limitations, but physically, we can build a structure any place on the planet and outside the planet. No question about it. So there's no height limitation. Yes.
Thanks, Les. I know you're a teacher. You've mentored many people. You've had a firm for many years. And I'm just curious to know a little, to talk about, like, what's the balance of, like, being a peer to the people you work with and a leader, both with your clients and with the firm you have? Like, what are the challenges of being a leader?
I don't know. I don't know really that I'm a leader. I always say people say you're forgiving. I don't think I'm forgiving at all. I think I just don't have very much that needs to be forgiven. I'm very accepting. And I like to work with people. Some people don't want to work with me. That's the way life is. But I think that if you really enjoy working with people, you can do anything. Our daughter, Karame, she's 33 years old. She went to school here in New York. And her high school was 1.5 blocks from where we lived. And after school, she and her fellow classmates, maybe 10, would go to her apartment, clean out the refrigerator, and Karame, our daughter, would get out her baton and wave it over the kids and get them to do their homework and like doing it. It's the last part that's really critical. And she's extremely successful as a product designer. Well, she's a good, excellent product designer, don't misunderstand me. But her real talent is getting the people who work for her, and she now has people all over, to get them to do what she wants them to do and to like doing it. And if you can do that, you can accomplish anything. I say to my students, you talk about that, I say to my students, you're not in the architecture business or the engineering business, that's not what you are. You're in the communication business. If you can't communicate, forget it. You're never going to get it. And by communicating, I'm not talking just about the verbal skills. You can't have lunch with Ian Pei if you can't talk about wine. No, I'm serious. It's impossible. I mean, or food, or the theater, or what. I mean, you have to take the time. You have to get out from behind your computer screen and get involved. People bitch about Donald Trump, and I say, forget about it. We have an election coming up in 1.5 years. Going to change the whole House and 1/3 of the Senate. If you don't like Donald Trump, get out and work to change it. Don't talk about it. Work at it. I'm a workaholic. And Sati, my wife, is also a workaholic, unfortunately.
I think we should thank Les and Sati. Wine, we have some here, so it's a theme of the evening. So we have books and we have wine and water as well. So please partake, buy a book, but partake of the wine. And thank you for coming. Carol Willis. I'm the founder, director, and curator of the museum. And I hope that you'll, if this is the first time you've come, like Sandy, that you'll come back many, many more times, because we do programs like this, but if you were here an hour earlier, you would have seen the exhibition that occupies the center of the space, and know that we explore topics in high-rise history from New York to around the world, from the first years of the history of the skyscraper, which is this one, 1874 and forward, to the present and the future of tall buildings. So, and we've been here in our space for going on into our 14th year, but it happens that this is our 20th anniversary of the founding of the museum, which we did in vacant space on Wall Street, the first one at 44 Wall Street, back in 1997. So in the spring of 1997, we put up a first show called Downtown New York, the Architecture of Business and the Business of Buildings. And soon, and that's what this card is that you can also use as a fan, which is what I'm going to do, Millennium, Lower Manhattan in the 1990s is the show that will go up in a week or two. And we'll look back at the history, the recent history of New York in the 1990s, especially of downtown, at a time when Lower Manhattan was being reinvented, as it was being vacated by the many banks who were merging, as it was on the skids in the real estate industry because of the stock market crash in 1887 and the savings and loan crisis that went into the 90s. And as we know, as denizens of Wall Street or Broad Street in the financial district, as Les and Sautina and the museum were at the time, there was like no market for real estate, and architects and engineers began to occupy some of these taller buildings. So we're going to look back at Lower Manhattan in the 90s in a time looking towards the millennium, which is the title of the show, when it seemed like downtown was changing enormously, and that it was it was being reinvented into a new identity. And the millennium seemed like a time to look both back at the past of the 20th century and forward into the 21st century. So for historians and people who are writers and self-conscious about historical change, 2000 seemed like a propitious year. Little did we know that the cataclysmic change in the history of New York and the history of America and the world would be in 2001 and not in 2000. So the idea of looking back at a time before we knew 9/11 would happen is part of what we're exploring in this exhibition. And I mentioned the 20 years and us being on Wall Street in our first show because it was, I think, almost exactly 20 years ago that I met Les. And I remember very clearly not knowing you, but feeling comfortable with you right away when we were all standing up on the new bar, the greatest bar in the world, at the top of the World Trade Center. And Bob Stern was with us at the time too, because we were all celebrating the debut of Hugh Hardy's, the late great Hugh Hardy, much missed. New designs for this great bar and this great people space. And Les and Bob were there, and we were kind of waiting to go through the space, and we were talking about, I'm starting the Skyscraper Museum, and Bob said, I want to be on the board, and Les said, I want to be on the board too. And I said, wow, these two guys want to help, make this happen. And they did, and Les especially was always there in order to help me understand the engineering aspects of both the history and the present of skyscrapers, of tall buildings, because as a historian I was very unschooled in these things. And so I've always found engineers, Les especially, but all engineers, to be enormously generous in being didacts about what they do as engineers, helping people understand the dynamics and the structure of buildings. So I owed a great debt to him in every way that he has contributed to the museum, and that idea of understanding and so explaining an engineer's perspective on the world and how you look at the world, how you make decisions, how you design, like the structure of design, the title of his book, and an engineer's, and I have to say, yes, an extraordinary life in architecture. So most of you, I mean, many of you, majority of you have known Les for some time, of colleagues who've worked with him, are friends, and so, and a lot of you have probably never heard him speak before, don't know him, haven't had the pleasure. So this talk will be kind of half professional and half popular, and that's the idea. This is actually one of the Skyscraper seminars, as we call them, that is kind of designed for professional audiences, but we want it to be open to everyone who's interested. So with that little bit of personal and professional introduction, here's someone that I think most of you know well and admire enormously, Les Robertson.